Okay, so we have three cases when we use the method that we introduced in the introduction. Let's take a second order linear homogeneous differential equation with constant as their coefficients, and we assume y is equal e to the mx, and let's recall its first derivative is you take m out, m e to the mx, and let's write down the second derivative, you take another m out, so m square e to the mx. So when you substitute them into the differential equation, we got this quadratic formula, a2m square plus a1m plus a naught is equal to 0, a quadratic function. Now to solve this for m, you can use factorizing or quadratic formula, but let's say once you do that, you get two distinct roots. That's the first case. You can find m1 and m2, two distinct roots. Now, if you can find two distinct roots, your solution or your fundamental set of solutions will be e to the m1x and e to the m2x. Now, these two are two linearly independent functions when m1 and m2 are different. Okay. Alright, then we can write the complementary solution, complementary function, the general solution as y is equal to c1 times e to the m1x plus c2 times e to the mx. Okay, that's the first case. Let's look at some examples. Okay, so the first example in the node. So we assume y is equal to e to the mx. We saw these things and let's substitute them. So y double prime will be like m square e to the mx. Plus 4 times y prime is m e to the mx. This should be equal to 0. Now we factorize e to the mx out because that's common. So m square plus 4m e to the mx equal to 0. And we know e to the mx is not equal to 0. It is never 0. So m square plus 4m have to be 0. Now you tell me, what are the two m values here? Can we factorize this here? Yes, this is the simplest quadratic equation you can get, right? You can factor out a m out. So m times m plus 4 is equal to 0. So what does it mean? Either m is 0 or m is negative 4, right? So we have two distinct values for m. Great. What is the fundamental set of solution? E to this is, let's call this m1, let's call this m2. E to the 0x and e to the negative 4x, right? So this is same as what? E to the 0x is 1, right? Second one is, well, we cannot simplify the second one. So you can see these two are two linearly independent functions. Great. What is the general solution? Here's the general solution. C1 times 1, it's just C1, plus C2 times e to the negative 4x. That is how we solve a problem when we have two distinct roots. Easiest case. Isn't this easy? Right? It's all about factorizing, okay? Or using the quadratic formula to factorize. Let's look at another example. So y is equal to e to the mx. So let's substitute that into the second example, okay? I might need more space. So when I substitute m square e to the mx, that is the second derivative, plus 5 times m e to the mx, that's the first derivative, plus 6 times e to the mx is equal to 0. So we do the same thing, factor out e to the mx, m square plus 5m plus 6 equal to 0. E to the mx is never 0. Now as a good student, you should write it down when you write the answers, right? Because that's the correct argument. So that means m square plus 5m plus 6 should be 0. Now, how can we solve this for m? You can factorize or you can use the quadratic formula. Any way you like, okay? I find it that here using the factorizing will be easy, right? 6 is 2 times 3, right? So 5 can be created 2 plus 3. So this is m square plus 2m plus 3m plus 6 equal to 0. So if you factorize this, you get m plus 2 from here. Here if I factor out 3, this will be m plus 2. So the factorizing will be m plus 2, m plus 3 is equal to 0. Great. So what are the two m values? M1 is negative 2 and M2 is negative 3. Or you can choose M1 to be negative 3, M2 to be negative 2. The order doesn't matter, okay? Fantastic. All right. Now, here's a mistake students can do. Once you come to here, students think, oh, M1 is 2, M2 is 3. No, okay. M1 is actually negative 2. The M value that makes this term 0 is negative 2, right? The M value that takes this term 0 is negative 3, right? So be careful with that. So what is the fundamental set of solutions? Okay, e to the negative 2x from here and e to the negative 3x. That's the fundamental set of solutions. Now, what is the general solution? Y is equal to C1 times e to the negative 2x plus C2 times e to the negative 3x. Isn't this so easy? Okay, practice the factorizing, okay, or you can use the quadratic formula, whatever you like. But here, before we finish, it says use the initial, subject to the initial condition. In the question says we have initial conditions. Now, why do we need initial conditions? Well, to find C1 and C2. So the first condition, it says y0 is 0 when x is equal to 0, y is 0. So if we use that here, y is 0, when x is equal to 0, e to the 0 is 1. Here also 1, right? When you substitute 0 for x. So it's 1 times c1 plus 1 times c2. So this is the first equation. Okay, so then let's use the second condition. Second condition, it says y prime 0 is 1. Now you need y prime. So you know y. How can we find y prime? Well, you have to differentiate this. So y prime first will be, if you differentiate this term, negative 2 comes out. So negative 2 c1 e to the negative 2x. Plus if you differentiate the second term, negative 3 comes out. Negative 3 c2 e to the negative 3x. Now let's use the initial condition, second one. So y prime 0 means you substitute 0 for x, then you get 1 for y. So 1 here, negative 2 c1 e to the 0 is 1 minus 3 c2 e to the 0 is 1. So this is the second equation. So we have two equations, don't we? c1 plus c2 is equal to 0, negative 2 c1 minus 3 c2 is equal to 0. So how can we solve these two equations? Well, let's multiply this first. Let's label them first and second equation. Let's multiply the first equation by 2. Okay, so then we get 2c1 plus 2c2 is equal to 0. That's the first equation. Multiply by just 2, okay, number 2. Then the second equation is negative 2c1 minus 3c2 is equal to 0. Now you see why I multiplied by 2, because when let's call this third equation, let's call this second equation, because we change the first equation to be third equation by multiplying by number 2, just a number 2, okay, not by second equation. Now let's add 3 and 2. So if you add equation 3 and 2, c1 cancel out, right? So that is why I multiply it by 2, so that, because I foresee that, well, if I had 2c1, when I cancel them out. Or if I had negative, you can multiply by negative 3 and can multiply by 3 and cancel out c2 also. That's also possible, okay? Alright, so when you add, c1 cancel out, 2c2 minus 3c2, adding means, well, this negative doesn't change. Oh, here this should be 1, right? I think, yeah. Here it said it was 1. Yeah, because I copied that condition wrong. Okay, so it's 1. So 2 minus 3 is negative 1. Negative 1 is c2 is 1. So c2 is negative 1. Fantastic. So if c2 is negative 1, what is c1? So c1 plus c2 is 0. So that means c1 is 1, right? c1 is 1, c2 is negative 1. So we can write the final solution. So the general solution we found, y is equal to c1 e to the negative 2x plus c2 e to the negative 3x. So y, now c1 is 1, so e to the negative 2x plus c2 is negative 1. So let's have minus here, e to the negative 3. So this is the unique solution for that differential equation. Anyway, to summarize, you get the auxiliary equation, you factorize it. If you get distinct roots, two different roots, you write the generals, you find the fundamental set of solutions as e to the m1x and e to the m2x. Okay, all right, thank you.